All right, let's dive in. Today, we're tackling something pretty big, something that's always fascinated me: quantum time.
Oh, yeah. We're going deep on this one.
Our listener wants to know, what even is quantum time? Is it different from how we normally think about time, and what does it all mean? Thankfully, they've sent us some excerpts from Exploring the Quantum Nature of Time as a starting point.
A great book.
And before we get lost in the quantum weeds, maybe we should start with something a bit more concrete: Planck time.
Right. Planck time. That's like the tiniest tick of the universe's clock.
Yeah.
It's unbelievably small, like 10 to the power of negative 44 seconds. It's almost impossible to even grasp how small that is.
I mean, that's way beyond anything I can imagine. And at that scale, is that where things start to get really strange? I mean, we experience time as this smooth flowing thing.
Exactly. And that's where things get interesting. In the quantum realm, time might not be so smooth. It could be grainy, even discontinuous. Imagine like a film strip. We see the movie as a continuous flow of images, but it's really just a bunch of still frames, right?
Right.
So Planck time could be like those individual frames, the most fundamental units of time possible.
Whoa, okay. So you're saying our experience of time as this smooth thing is kind of an illusion.
Possibly.
Yeah.
Now, you also had a great question about different time zones within an atom. You're curious about the time scales of, say, quarks and molecules, and if it's like experiencing time dilation at those tiny levels.
Yeah, it's like I picture each particle having its own little clock, ticking at its own rate.
I love that image. And while it's not exactly time dilation in the relativistic sense, like what happens near a black hole, different parts of an atom do operate at vastly different frequencies.
Hmm.
Imagine a bustling city, right? Each district has its own rhythm. The financial district, let's say that's our quarks, buzzing at super speed, while the residential areas, the molecules, have a slower pace.
So in a single atom, we could have these different time domains. That's wild. Speaking of wild, what about this thing called temporal entanglement? You mentioned a quark influencing a molecule state at a later time. It's like spooky action, but through time, not just space.
Exactly. We're so used to entanglement in terms of space, two particles linked across a distance. But temporal entanglement, that suggests connections across time. Two people, linked not by distance but by time. One in the present, one in the future, their actions intertwined.
Oh man, my head is spinning. It's like saying the future could influence the present.
Which brings us to your family story, the one about those job opportunities. It seems like things aligned because of future need, like the universe was preparing for what was to come.
Yes, my mom always said those missed job opportunities were actually good things. They kept me free for a family situation that happened later. It's like those past events were shaped by that future need.
And that really echoes the idea of retrocausality in quantum mechanics, the idea that the future can influence the past. It challenges our linear view of time. Time is a one-way street, and it opens up some pretty mind-blowing possibilities.
It's like the universe is playing a cosmic game of chess, making moves across time. This is incredible. So, while we're on this mind-bending train, could we talk about Wheeler's delayed choice experiment? There seems to be a connection to my family's experience there.
Absolutely. Wheeler's delayed choice experiment is one of those things that really makes you scratch your head about time and cause and effect. Imagine a photon, a particle of light, heading towards two possible paths.
Okay.
Now, the experimenter gets to choose which path to measure after the photon has already started its journey.
Hold on, how does that even work? The photon has already chosen a path, hasn't it?
That's the weird part. Somehow, the photon's behavior seems to be influenced by a choice made after it's entered the apparatus. It's almost as if the photon knew in advance how it would be measured.
This is really stretching my understanding of time. It's making me think of, Doctor Strange and his time stone. Are there any real quantum phenomena that even slightly resemble that?
Funny you should mention that. You brought up the quantum time mirror and the quantum eraser. These are real phenomena that, while not quite time manipulation on a Doctor Strange level, do show some amazing control over events at the quantum level.
Okay, I'm hooked. Let's start with the quantum time mirror. What's that all about?
Imagine a pebble dropped into a pond, ripples spread outward, right?
Yeah.
Well, with the quantum time mirror, we're talking about applying energy in a very specific way that makes those ripples converge back to where they started.
Wait, so we're talking about reversing events at a quantum level? That's insane. And what about this quantum eraser? How does that work?
Okay, think of a classic mystery novel. You're convinced the butler did it.
Ah.
All the clues point to him, right?
Right, but then there's a twist.
Exactly.
Yeah.
Some new piece of information comes up, changes everything.
Like, oh, the butler has an identical twin. Suddenly, all those clues become totally ambiguous.
Exactly. The information that seemed to solve the mystery gets erased, and we're back to square one. In the quantum world, the quantum eraser does something similar. It erases information about a particle's path, restoring a system to a state of multiple possibilities.
So if we apply that to my family story, the new information about my uncle's future needs acted like a quantum eraser, changing how we viewed those past job opportunities. It's like a reframing of the past based on new information.
Exactly.
This is all so fascinating, but let's push this Doctor Strange analogy a bit further. He's manipulating time on a massive scale with that time stone. Could we ever scale up something like quantum erasure to work on, big objects?
That's the big question. Theoretically, maybe, but there are some huge challenges. For one, we'd need to figure out how to maintain quantum coherence in larger objects.
Yeah, because usually things at our level lose those quantum properties super fast, right? It's like trying to stop a souffle from collapsing.
Precisely. Decoherence is a major roadblock. And then we'd have to track and manipulate huge numbers of entangled particles way beyond what we can do now.
So not as easy as Doctor Strange makes it look, but you mentioned another interesting point about him, absorbing Dormammu, which makes me think about brain-computer interfaces, BCIs, working at a quantum level.
Right. Imagine a BCI that can read and translate those neural quantum states, letting us interact with the quantum world directly. It'd be like having a direct line to the fabric of reality itself.
Wow, that's incredible. But how could that even work? What would that interface even look like?
Well, that's where we get into some really speculative territory. But one possibility is that our brains already have a natural quantum interface. Remember the Penrose-Hameroff theory we touched on earlier?
You mean the one about microtubules acting as quantum computers in our brains?
That's the one. The Orch-Orr theory suggests that these tiny structures in our neurons could be maintaining quantum coherence, even at body temperature, something we could barely do in the lab.
So our brains might already be tapping into the quantum world. Amazing. But how could a BCI access that? How could we control those quantum processes?
That's the challenge, right? We need to decode the language of these microtubules, figure out how they handle information, how they keep things coherent, how they interact with the regular world of neurons and synapses.
So we'd be reverse engineering the quantum processes in our own brains. This is getting very meta. Maybe we should pause here and let our listeners digest all this before diving into the really weird stuff in part 2.
Yeah, good idea. We've only just scratched the surface. Okay, so we've been talking about some pretty mind-bending stuff, haven't we?
Yeah, mind-bending is a good word for it. I'm still trying to grasp this idea that our brains might be acting like quantum computers. It's like we're carrying around these super powerful processors in our heads and we're just starting to figure out how they work.
Right. It's fascinating. And a big part of that is the Penrose-Hameroff theory. The idea that microtubules, those tiny structures inside our neurons, could be the key to consciousness itself.
It's not just that quantum stuff is happening in the brain, but that it might actually be what makes us, well, us. Our thoughts, feelings, everything.
Exactly. It's a radical idea, but it's gaining traction. If it's true, it completely changes how we think about the brain and consciousness.
Okay, so let's zoom in on those microtubules. What are they and how could they possibly be quantum computers?
So picture these tiny tubes, really tiny, about 25 nanometers across, running all through our neurons. They're made of these protein subunits called tubulin, and these proteins can switch between different states.
Like little switches flipping on and off.
Perfect analogy. And according to the Orch-Orr theory, these tubulin switches can be in a superposition of states, a classic quantum thing. It's like each tubulin molecule is both on and off at the same time.
Wait, but doesn't quantum stuff usually need like super cold temperatures? How could these delicate quantum states survive in our warm, messy brains?
That's a great question, and it's one of the big mysteries surrounding the Orch-Orr theory. Penrose and Hameroff think the unique structure of microtubules, along with water molecules inside the neuron, might be shielding those quantum states, keeping them coherent.
Because these microtubules are like little fortresses protecting the quantum stuff inside.
Exactly. But it's not just protection. They have to communicate too. The theory says these quantum states in microtubules can get entangled, not just with each other, but maybe across huge networks of neurons.
Whoa, so we're talking about this massive web of quantum entanglement inside our brains. That's wild.
That's what the theory suggests. And when these entangled states collapse, that's what triggers moments of consciousness.
It's like our brains are orchestrating this huge symphony of quantum events, and those events are what give us our experience of the world.
I like that, a quantum symphony. Now, remember, you were interested in the idea of a BCI, a brain-computer interface that could tap into all this. It's a mind-blowing idea, but also the technology is still way out there, you know?
Yeah, for sure. But if we could crack the code of these microtubules, figure out how they work, how they maintain coherence, wouldn't that be incredible?
Oh, absolutely. Imagine being able to interface directly with those quantum processes in the brain. We could potentially treat neurological diseases, enhance our abilities, even expand our consciousness beyond what we know now.
It's like tapping into the source code of reality. Okay, but how do we even start? How do we build a BCI that can interact with these tiny, delicate microtubules?
It's a huge challenge for sure. But one approach is to think about bio-inspired quantum computing. Instead of forcing our current technology onto the brain, what if we learn from how nature has already solved this problem?
So like building systems that mimic microtubules.
Exactly. We could use organic molecules like tubulin that have quantum properties at room temperature. We could build nanostructures that assemble themselves into complex patterns, copying the microtubule's structure.
So we'd be like growing a quantum interface instead of building it.
I like that. And once we have this bio-inspired hardware, we need to develop a way to communicate with it. A language, a set of protocols to understand how it processes information, how it responds.
This all sounds amazing, but also really complex. Where would we even begin?
One way is to look at nature again. Those error correction mechanisms we discussed earlier, biological systems have developed these amazing ways to maintain coherence, to prevent errors in these quantum systems.
So we can study microtubules, learn how they do it, and try to build artificial systems that can do the same.
That's the idea. It's about being inspired by nature's ingenuity.
Okay, this is really blowing my mind. Let's say we do manage to crack this code, build this bio-inspired quantum BCI. What could we do with it? What would be the real-world applications?
The possibilities are endless. Imagine treating neurological diseases by directly manipulating those quantum processes in the brain. We could reverse Alzheimer's, Parkinson's, spinal cord injuries.
Wow, that would revolutionize medicine as we know it.
And it's not just healing. We could enhance cognitive abilities, improve memory, boost creativity. We could even expand our consciousness beyond what we thought possible.
We're talking about unlocking the full potential of the human mind.
Exactly. Imagine a world where we could access that vast, untapped power within us. It would change everything.
This is incredibly exciting, but also a little scary. I mean, are there downsides? What about the ethics of manipulating consciousness on such a deep level?
You're right. Those are important questions. We have to proceed cautiously, ethically, and responsibly. But the potential benefits are so huge, we can't ignore them.
It's like we're at the edge of a new era, an era where technology and consciousness are merging, and the possibilities are limitless.
And as we explore this uncharted territory, who knows what we'll find?
Wow, we've covered some serious ground in this deep dive. Quantum time, microtubules, brain-computer interfaces. My head is spinning.
I know, right? It's a lot to process, but it's also incredibly exciting. These are some of the biggest mysteries we face. Time, consciousness, the nature of reality. It's no wonder we're drawn to them.
Absolutely. But the more we dig into these quantum ideas, the more challenges we seem to uncover. Like you mentioned earlier, building a bio-inspired quantum BCI is a massive undertaking. What are some of the biggest hurdles?
Well, maintaining quantum coherence in these bio-inspired systems is a huge one. Quantum states, they're incredibly fragile. The slightest interaction with their environment can disrupt them. It's called decoherence.
So it's like what, trying to balance a stack of coins on a vibrating table?
Pretty much. And it's even harder when we're talking about systems that operate at room temperature, like our brains. The quantum computers we have now need those super cold temperatures in carefully controlled environments just to keep things coherent.
So how do we solve that with these bio-inspired systems? How do we prevent that decoherence?
That's where we need to turn to nature for inspiration. Biological systems, like those microtubules we talked about, they've figured out how to maintain coherence at our body temperature. They've been doing it for millions of years.
So we need to figure out how they're doing it. Crack their code, so to speak?
Exactly. Study their structure, how they interact with their environment, how they protect those delicate quantum states. It's like reverse engineering millions of years of evolution.
Wow, that's a pretty tall order.
It is. And it's not just about preventing decoherence. We also need to learn how to control those quantum states, manipulate them. If we're going to build a BCI that can actually interact with microtubules, we need to speak their language.
So we're talking about developing quantum tools that can work with these biological quantum systems.
Exactly. Tools that can read the information stored in those quantum states, write new information, even trigger specific quantum events. It's a delicate dance between biology and technology.
This is incredible, but it also raises some ethical questions. I mean, we're talking about manipulating consciousness at its core. What are your thoughts on that?
You're absolutely right. Those ethical considerations are paramount. We can't just rush ahead blindly. We need to think about the potential consequences, both positive and negative. The potential for misuse is definitely there.
It's a huge responsibility. We're not just talking about some new gadget here. We're talking about shaping the future of humanity.
And that's what makes this all so important. This isn't just about exploring the mysteries of quantum time. It's about understanding what it means to be human in a world where technology and consciousness are becoming intertwined. It's about making sure we use this knowledge wisely.
Well, I think that's about all the time we have for today. But I have a feeling this conversation is far from over.
Definitely not. The exploration of time, consciousness, the nature of reality, that's a journey that never truly ends.
And to our listener, we leave you with this thought to ponder. If our consciousness is indeed rooted in the quantum realm, what does that mean for us? What does it mean for our free will, our understanding of reality, the future of our species? Keep questioning, keep exploring, and keep pushing the boundaries of what's possible. Until next time.